The next speaker for this session is from Leo from MIT, who will tell us about the effective theory of the synchronic fluid.
Okay, again I will start by thanking the organizers for inviting me to speak. And I'm going to talk about some work we did last year and also something to appear with two MIT students who just graduated this year. So let's consider, say, long wavelength disturbance of a system in thermal equilibrium. And the subsequent evolution of such long wave disturbance depend on very much on whether this is concerning a non-conserved quantity or conserved quantity. Say, suppose it's a non-conserved quantity, then those quantities can relax essentially at every point locally, and then the relaxation time is very, very short. So essentially just the typical mean-free time. But if it's a conserved quantity, then because of course the global constraint, then cannot relax locally and can relax only via transport. Then this is similar to the situation like a Goldstone boson. So that means actually when you consider the case infinite, say long wavelength excitations, and then the relaxation time will tend to go to infinite. And so that means that associated with conserved quantities, you will always find gapless and long-lived excitations. And actually, in the generic medium, these are the only gapless and long-lived excitations, and so they should be our focus to understand the low energy physics. And so just as a theory of Goldstone boson, there should exist a universal low energy effective theory about those modes. Of course, such a theory is already known. At phenomenological level, this is just hydrodynamics. And the hydrodynamics is the equation motion of hydrodynamics is just the conservation of conserved quantities like the stress tensor or if you have any other conserved current. Essentially, you just express your stress tensor and conserved current in terms of those dynamical variables, say inverse temperature, velocity, or chemical potential, which are assumed to be slow in varying function of surface time, and then you just solve those equations. And of course, this formalism is extremely powerful. Essentially controls every aspect of our life, and also what's happening in the solar system, or maybe in the evolution, say, of the galaxy or large-scale structure. And most recently, say, during last decade, has also been discovered that hydrodynamics plays a very important role in understanding the evolution of quark-gluon plasma created from, say, heavy ion conditions. And also people discovered that the evolution of cold atom systems, they also obey hydrodynamics. And actually just earlier this year, just a couple of months ago, it was discovered that actually graphene, electrons in graphene, they flow, they don't behave ballistically, they actually flow like water. Okay, so hydrodynamics is extremely powerful. But despite this known and a glorious history of hydrodynamics, there's some significant defect of it. So one important defect is that it does not capture fluctuations. But of course, statistical fluctuations are always there. So in this room, there will be fluctuations in the air density and the temperature. And such fluctuations can be important in many physical contexts. Say here, just to mention a few. Right now, there's a phenomenological approach to include the fluctuations into hydrodynamics, which was due to the Landau-Lifshitz. Is so-called the stochastic hydro. So essentially, you just add to your standard hydrodynamics equation some stochastic laws. So this psi mu or zeta stochastic laws, which you assume they satisfy some Gaussian distribution, etc. But this formulation is only good for linear equivalent disturbances. So if you have a linearized theory, and then such a theory, if you have a linearized disturbances, then such a theory works perfectly. but they are not adequate if you have far from equilibrium situations. And one of the most well-known far from equilibrium situation is this century-old problem called the Rayleigh-Ballard problem, which actually can be considered also as a model for this room. So suppose you have air conditioning on the top of the room, and then you have this situation, you have cold, say you put your system between two plates with the, say, two different temperature, and the bottom is hot and the top is hot, top is cold. And when the temperature difference is not big, then you have a then you have a stationary state, then you just have a stationary temperature gradient across the room. But now if you increase the temperature difference between the top and bottom, and then of course we also know, and then the system can develop convection. And the onset of this instability from this stationary state to this convective state is controlled, is essentially driven by hydrodynamic fluctuations, and you need, and in particular, the hydrodynamic fluctuations become essentially infinitely large near this non-equilibrium phase transition between this stationary state and this convective state. And we need such a theory in order to describe such a, say, phase transition property. And another defect with hydrodynamics is that the current formulation of hydrodynamics is actually awkward from theoretical perspective. So a very important element of hydrodynamics is that you need to express your stress tensor or conserved current in terms of the dynamic variables, in terms of derivative expansions. But if you just write down the most general derivative expansion, say consistent with all the symmetries of your theory, it turns out that gives you the wrong answer. You will get more transport coefficient than observed in nature. So you actually have to fudge the answer. And of course, the fudge the answer, you just have to add the more phenomenological constraints. And again, this is due to Landau, is that the one such phenomenological constraint is you should construct entropy current, again in terms of the same kind of dynamic variables, and then you require that the solution of your equation motion must satisfy that at every space-time point, the divergence of your entropy current is non-negative. And also there's a constraint from the time, underlying time reversal symmetry, which is normally called the Onsack relation, which tells you that the linear response matrix must be symmetric. So those phenomenological constraints are very powerful and they work very well. But of course they are awkward because we are using solutions to constrain equation motions. And clearly there's something fundamental missing. We would like to write down our equation motion just based on a basic principle rather than using such phenomenological constraints. And also there are important questions, say whether we can actually find the microscopic origin of such constraints and whether also these constraints are complete or not. We will address these issues by developing hydrodynamics as a low-energy effective field theory of a general many-body system at a finite temperature. It's just like we write down the theory of pion just based on the spontaneous symmetry breaking. And again, here we will write down a low-energy effective theory just based on the conserved quantities. And the immediate consequence of this is that this leads to an action principle for the full fluctuating hydrodynamics, which are applicable to far from equilibrium situations, so that we can address, say, the problem of the phase transition, say, in this Rayleigh-Ballard problem. And many of you, of course, may know that the standard law of hydrodynamics, the standard law is that the dissipative systems actually don't have action formulation. Classically, this is true. Indeed, it's awkward to write down an action for dissipative system. But this question actually have a lateral resolution in quantum mechanics. So here we're interested in describing real-time dynamics, say around some state, and not say some transition amplitude. And so that means that we cannot use the standard path integral formalism, which say which corresponding to the transition amplitude. Then you just do your path integral from t equal to minus infinity to t equal to plus infinity. And instead, you have to use this so-called closed time path, which if you want to consider the expectation value in some state, say in some general density matrix, what you should do is you take your path integral from minus infinity to plus infinity, and then involve back, so that you take expectation value in the same state, okay, not as a transition amplitude. And such a formalism then will automatically take into account, say, dissipation, whatever dissipation or fluctuation in your state, in whatever the density matrix you are in. And so this is normally called the closed time path or Schwinger-Keldysh contour. And immediately consequence of this using this such kind of contour is that if you want to describe your system using a single time, so now you have to use two copies of your space-time. But you can also just consider all the fields living in a single space-time, and then that means you need to double the number of degrees of freedom. And with one set of degrees freedom, associated, say, with each leg of the contour. So here is the a rough picture. Here is the picture we have in mind what this effective theory means. So suppose you have a macroscopic description, say, of whatever, say some many-body system in the thermal density matrix, and we want to integrate out all the degrees freedom except those hydrodynamic modes, which are the only gapless and long-lived modes associated with the conserved quantities. And typically, say the UV cutoff is T, and then this path integral of the hydrodynamic modes then should capture all your low energy physics. And say you start with this theory, then you run your standard RG, and then you will get the you will get the macroscopic phenomenon. And so one thing I should mention is that if you are interested in the thermal state, then whatever the density matrix you are interested in is encoded in the effective action itself. Okay. So your effective action, so the coefficient of your effective action should reflect that you are in the thermal state. And also, the standard formulation of the hydrodynamics then would just correspond to the saddle point of this path integral. And it's like more like a mean field approximation to your path integral. And as usual, in your effective field theory, we need to have three ingredients in order to write down such a path integral. So the first is what are the dynamic variables. Okay? So it turns out, if you want to write down an action principle, and then the standard hydrodynamic variable like inverse temperature, velocity, and the chemical potential, they don't actually work. And so this you can easily do by trial and error. But there's one way to think about it, is that if you look at the equation motion associated with those variables, they actually first order in derivatives, say at the ideal fluid level. And you know, if you have an equation first order in derivatives, then it's awkward to write down the action formalism for them. Say, for example, as E and M, the equation motion for electric and magnetic fields are first order in derivatives, and then we have to go to the vector potential. And so we first have to identify what are the right degrees freedom to use here. And the second, we want to answer the question, what should be the symmetry we should impose in the action, okay? And then with the identification of the degrees of freedom and with the symmetry, then you can just write down the most general action compatible with them. But then the last, we have to specify, say, what should be the integration measure, because in general, this, And I should mention that the search for action principle, say, for dissipative hydrodynamics has been a long-standing, say, problem in mathematical physics. Attempts at dating back at least to the Hagelot in 1911, and over the years there are many attempts. Okay, and I should mention there's very recently there's an alternative approach proposed by Hill and Lagrangian and Ragazzani. So here, for conceptual simplicity, I will just describe the story for neutral normal fluids. And you can actually write down the theory for full charge fluid, which is in our paper. And this can also be generalized to superfluid. Yeah. So now let's describe what should be the dynamic variable. So now let's recall first the Lagrangian description of the hydrodynamics. So in the Lagrangian description of the hydrodynamics, he said you consider, say, a continuous medium, and then you associate a label for each element of your medium, okay? And so this sigma I just label your each fluid element. They go with your fluid elements. And then the hydrodynamics, the fluid motion of each element, then you just describe by a mapping of each fluid element to your physical space-time, to your physical space, okay? And then the function of this as a function of sigma and the t, then just describe the fluid motion. Okay, this is the Lagrangian way of thinking about fluid. So we have developed an integrating in procedure to identify the gapless and non-linear degrees freedom associated with conserved stress tensor. I will not give the detail here. I will just tell you the answer. And the answer turns out to be very simple. The answer turns out just to be a doubled copy of this Lagrangian description, okay, suitably generalized. So essentially, because now we are using this a closed time like curve, and so you have need to double your degrees freedom, so that means we have to introduce two sets of your space-time coordinates. But now I also introduce the internal time. Instead of using the physical time here, I also introduce the internal time, and now here, now this will be just the full physical space-time, okay? And so what you do is that you you just use those mapping, then you can just pull back your space-time metric, say, to this fluid space. Yeah. Yeah, so the picture is that we have a fluid space-time, and which are labeling the fluid and their internal time. And then you have two copies of your physical space-time, okay, because we have a double contour. And then, say, suppose you, say, fix the sigma I, you change sigma 0, and then this function just tells you your trajectory in your physical space-time. And also this picture also actually arises naturally from the holographic constructions from the picture of the liquid and the sun, and where this fluid space-time can be considered just corresponding to the horizon. And given this picture, then one can immediately write down how those variables are related to the standard hydrodynamic variables. And you can just get the velocity by taking the average of these two physical space-time and then take derivative over your internal time. Okay? And then that just gives you the velocity, and then you normalize this so that u squared equals to -1. And also we need to actually introduce a scalar field in the fluid. We also need to introduce a scalar field in this fluid space-time where would corresponding to the temperature. And then the difference of these two physical space-time coordinate then would be interpreted as the noise. So now what you do is you essentially just pull back your physical space-time metric to your fluid space-time, and then you try to write down the action for that, okay? But now we face a challenge, because we know that the fluid equation motion only depends on velocity. So your theory must be such, so your action must be such that when you write down the equation motion, the equation motion should not be expressed in x, but it should be expressed solely in terms of the velocity. And I emphasize this is only corresponding to equation motion and not corresponding to the full action. Yeah, full action can fluctuate, etc., but equation motion should be only expressed in terms of velocity. And then, for example, this is also a difference between the solid and the fluid, because the Lagrangian picture can also be applied to the solid, in which the x itself does appear in your equation motion. So now we have to impose the symmetry in your action for this to happen. Okay, So this is just remind you yeah. And now with this identification, there's now a very simple way to determine what should be the symmetry your action satisfies. So remember, the fluid can move. And the first symmetry we identify is that you should be able to, at a given fixed time, you should be able to relabel your fluid element. Okay? Since there's no fixed position for each fluid element, you should have the freedom to relabel them. And so we should be able to have a pure spatial diffeomorphism at a given time. And also, if you focus on each fluid element itself, then you should be able to have a full-time reparametrization symmetry associated with that, associated with each fluid element. And also, since in the liquid, the fluid element can move essentially independent of each other, and then this reparametrization symmetry should depend on your fluid element itself. They should have independent reparametrization of the time direction. And this symmetry defines what we mean by a fluid. And indeed, it turns out that this symmetry does metric for you. And when you write down the most general action compatible with those symmetries, and then you find that the equation motion can be solely expressed in terms of velocity and the temperature, and not in terms of this original x field. And then this recovers the standard formulation of hydrodynamics modulo phenomenological constraints. But now we still need to vary. And essentially, the full nonlinear fluid fluctuation dynamics now just become a problem in differential geometry, which will lead to impose independent spatial diffeomorphism and time diffeomorphism. And say you can write down the covariant derivative and the curvature tensor, etc. So here, in this system, you actually have two Ricci tensor, and there's also some torsion. And each of those tensors now corresponding to hydrodynamic tensors. For example, this torsion turns out just corresponding to the vorticity of a fluid. And this will be the full story in the usual situation. But here we are considering a system defined with a closed time path. But for any system defined on the closed time path, there are some global constraints on the correlation functions, just because the system is defined on this kind of path. So that means we have to impose additional symmetries, so that your offshore, so that we have to impose additional symmetry on your offshore action, so that these constraints due to this closed time path are satisfied after you do the path integral. Okay, and it's most convenient to write such kind of conditions in terms of your generating functional. So if you we are interested in the stress tensor, and the generating functional for the stress tensor just corresponding to you turn on the external metric for each leg of your space-time, for each leg of your contour. And say you can turn on different metric for each leg, and then in general can define down two space-time metrics. And when you take derivative of them, then you get various correlation functions of your stress tensor. So one immediate condition coming from this contour is the reflectivity condition. So if you take a complex conjugate of your path integral, then just corresponding to reverse the direction of your contour. And then that just equivalent, you just switch these two legs. Okay? It turned out this can be satisfied very simply just by imposing a Ricci reflection symmetry on both your dynamic and the background field. Okay? But this turns out to have very non-trivial consequences. It implies that your action actually is complex. In particular, when you have a complex action, then you must require the imaginary part of the action to be non-negative. Otherwise, your path integral is not well defined. Okay. So this implies this imposes some non-negativity conditions. And another condition comes from this path, comes from the definition we are interested in the thermal state. And any correlation function in the thermal state satisfies so-called the KMS conditions. And conversely, you can also use KMS conditions to characterize your thermal state. So that means that your theory must possess the symmetry so that this K-mass condition is satisfied. So K-mass condition, if I write it in terms of the generating function, I have the following form. It's now some kind of D2 symmetry on your generating function. So I will not give you the detail here. It turns out this K-mass condition can be satisfied by imposing a lot of Z2 symmetry on your action. So we call this a local K-mass condition. And here there's a lot of surprise. It turns out the combination of this fermionic symmetry plus this local K-mass condition, then there's a lot of emergent fermionic symmetry. And then in the classical limit, turns out in the classical limit, say if you are only interested in the classical statistical fluctuation, and then turns out that these now you have two fermionic symmetry, and now the commutator of these two fermionic symmetry leads to a standard supersymmetric algebra. Okay, so now you have an emergent supersymmetry. You have emergent supersymmetry. And now if you want, but at the quantum level, if you keep the non-zero H bar, then some indications that there's a quantum deformed supersymmetry with the following algebra. Yeah, so let me just summarize. Yeah, so the slogan is that if you have hydrodynamics with classical statistical fluctuations, and this is actually described by supersymmetric quantum field theory, and there's effective H bar, which is given by the standard entropy density, and this recovers the standard hydrodynamics, give rise to new constraints and new fluctuation dissipation relation, etc. But this also gives you a full nonlinear fluctuation dynamics. Yeah, just to show you, and this is a bosonic action for a full charged fluid, say, to the first order in derivatives. And hopefully we can use this theory, say, to apply to the airflow in this room. Maybe we can understand, maybe we can learn some new physics from it. And there are many future directions, and then I will stop here. Thank you. I don't know the answer. I don't know the answer of the question, but in principle, this provides a field theory framework now to deal with questions like turbulence or the scaling in the turbulence. Say in the old days, the Soviet people, they have observed that the turbulence phenomena, they have very many common properties with quantum field theory, and people have been searching for quantum field theory description, say maybe for turbulence. And I don't know the answer, but I think this potentially provides a framework to do that.
Do you have an example of a new relation between transport coefficients that comes from your nonlinear Onsaga relations that was not, that didn't follow from entropy positivity or partition function and so on? For instance, if you go to second order for ordinary uncharged fluid, entropy positivity gives you 8 independent coefficients. Are these 8 related? Do they have further relations?
Right. So at second order, if you have a neutral fluid, that does not seem to give rise to new relations. But at second order, if you go to charged fluid, we believe you should. We only look at a baby version of it. You only look at the charge factor. And if you only look at the charge factor, when you go to second order in derivatives, then there appears to be new relations which is not captured by the linear Onsaga relations. Yeah, but we haven't done the full charged fluid analysis.
So you have a supersymmetry. So what are the fermionic degrees of freedom?
So what do you mean by what are the fermionic degrees of freedom?
When you are interpreting the supercharge as the symmetry of the theory, right?
Right.
So you have the velocity, for example. Then you have a super partner of the velocity.
Yeah. So those essentially, the physical interpretation of those fermions, essentially they're just some way, they're just some convenient way to parameterize, I think, your Path-integral measure. To parameterize your Path-integral measure so that you satisfy this unitarity condition. And I should say, the full story, I don't fully understand the. I should say, don't have a full picture of the supersymmetry here. Yeah, we just find we just find that there's an emergent supersymmetry. How to really properly think about this supersymmetry and the full content of this supersymmetry is still under exploration. Yeah, so I don't know. Yeah, but potentially we might, since we impose here as a global symmetry, we might be able to see the signature of such kind of anti-commuting degree of freedom.
Yeah, I suggest to thank, yeah.